Yeah, please check.
Yeah. Okay. We received the notification, so it should be fine. Oh, now let's see how can I. Yeah, exactly. You see, I cannot close this now. That's stupid. Okay. Yeah. I think we can start now. So yeah, hello everyone. Welcome to a new lecture in this seminar in computer architecture. My name is Juan. I'm one of the lecturers of this course and also senior researcher in the Safari research group with Professor Onur Mutlu. And this is one of the things that I work on, memory-centric computing, or as I said earlier, systems with processing in memory capabilities. There is a problem with Zoom? Why is that? It's looking good, no? The bar? Oh, I see, I see. Okay, can you switch? Great. Yeah. Now these guys in the room are going to see the next slides. So that's a problem. I think I should start sharing again.
Yeah, I thought the Safari laptop had this figured out, but I think you need to.
There is always an issue.
Yeah. Oh, okay. If you use slideshow, maybe you'll fix it now.
Yeah. Go there, swap. This is the limitation.
I mean, it's good to see what is coming next, but I don't need it. It's fine.
I think if you use slideshow, that should have worked instead of swap displays.
We did that.
Oh, okay.
Okay, sorry, Juan.
Okay, yeah, I hope it's more or less okay. And now, so yeah, let's start. As I said earlier, today we are going to talk about memory-centric computing. These are systems that solve one of the key problems, if not the biggest problem that we have today in computing systems. And this is the problem. Computing is bottlenecked by data. We are going to, first of all, motivate and explain what this means and why is this happening. And then we will start discussing potential solutions to this bottleneck and this problem. The thing is that nowadays data is key for many different important workloads like AI, machine learning, genomics, etc. And all these important workloads are very much data intensive, right? And one problem that we have is that usually we require to process this data very quickly and in an efficient manner, right? But okay, we can try to do that. We can design systems for that. But in the end, these systems may become overwhelmed very quickly. The reason is that data keeps increasing over time, right? So we are generating more data than the amount of data that we are able to process. And this is one pretty interesting example, the evolution or the recent growth of neural networks. You can compare some networks from 2018 and how in just about 2 years, the number of parameters in these networks, the number of weights in these networks has essentially increased by 1,000. And the trend doesn't seem to be going to change. So things are probably going even worse. This slide, it's from Sean Lee, as one of the founders of the Cerebras company. Cerebras is a company that fabricates a very large accelerator for machine learning. And this is one of the slides that he uses in his talks for motivation. He delivered one seminar last year, actually not last year, I think it was this year in February. And if you want to watch it here, you can access the link. But as you see, neural networks or machine learning are just an example of how data is growing these days. And it's not the only good example that we can offer. There are others as well in memory databases, graph and tree processing, in memory data analytics, and data center workloads. In all of these, data is leading to performance and energy bottlenecks. So data is overwhelming the computing systems. And that's not only in, like these server class applications we had in the previous slide. It's something that we can also find in mobile devices or in edge devices. And here you have some more example. Google Chrome, TensorFlow Mobile, or the BP9 encoder and decoder, right? So these are, let's say, more typical workloads in mobile systems or in consumer workloads in mobile systems. And there we also see that data leads to performance and energy bottleneck. And to give you even more examples, this is from the bioinformatics field. You have probably seen this slide earlier. Maybe Mohammed showed it last week. As you see, the speed at which the sequence data, right, like sequence genomes, has been evolving in the recent years, has grown in speed as since you see since the development of high throughput sequence technologies back in around 2008 or 2007, we have seen how the cost per megabase has changed a lot. And based on that, and due to that, the number of genome sequence has increased a lot. And if you look at this plot, for example, in just 3 years, we see like an increase by 8 times. So it's increasing very, very fast and essentially at an exponential rate. So also in genome analysis, data leads to performance and energy bottleneck. And this is another example. This is a paper from our group studying nanopore sequence technology, and an analysis of the state-of-the-art bottlenecks and future directions. And this is also a good reference to see how data is leading to performance and energy bottlenecks. And one of the problems that we have with genome analysis, and as I said, you have probably seen this earlier, is that we have special purpose machines for data generation, which is supposedly fast, even though it's not so fast, but the machine is dedicated to that, right? It's designed to do so as fast as possible. But later, we are analyzing that data using general purpose machines like CPUs or GPUs. And in the end, this leads to slow processing as well. So that's one of the things that we try to solve with our research. And here you can see like a very good example of different directions on how to accelerate genome analysis in this paper that Mohammed wrote in 2020. And indeed, we have some work already in this direction, the direction of having more specific architectures for sequence alignment, for genome alignment, right? And this is a pretty good example of them. An FPGA-based near memory acceleration framework for modern data-intensive applications, including some bioinformatics workloads. So over the course of the lecture, please don't hesitate to ask any questions. Just raise your hand. I will eventually ask you if you have any questions, but don't hesitate to stop me. So data overwhelms modern machines, and this affects the storage and memory capability, the communication capability, and the computation capability, which in the end are the, say, biggest components or most important components of the computing systems. So in the end, data overwhelms the system and impacts robustness, energy, performance, cost, etc. Why the 3 components that we were mentioning earlier? Because they are the 3 key components, or the, let's say, main components of the computing system, right? The place where we do computation, the means that we use for communication, and the place where we store the data and the information. And this is what John von Neumann and his collaborators defined back in 1946, right? The system, the computing system, is composed by a memory and storage or storage unit where we store the data, and then a computing unit where we process the data, right? Then in order to process the data, we first need to access data in memory and storage, and this is something that we do with the communication unit, right? And this is where indeed the key problem, or one of the key problems with data, resides in current computing systems. The fact that we need to move back and forth data between the memory and storage units and the computing units. But the problem is not that itself. It's not that we have to move data. The problem is that this communication unit that we use for data movement is typically very narrow, right? And because it's very narrow, this is like a funnel that is, you know, in some way, yeah, bottlenecking is like the bottleneck when moving the data from here to here, back and forth, right? So, yeah. And this happens in current computing systems, even though a lot of the computing system is devoted to data, either to store data or to move data. This is a relatively simple or toy representation of a computing systems or a CPU, a multi-core CPU. As you see, it has 9 cores that are depicted in red, but the rest of the components are memory. Either shared L2 cache or shared L3 cache, or the shared memory control to access an external shared memory. All of these shared, might not be shared, by the way. Inside the cores, we typically have private L1 caches, right? But in the end, what this is showing is that most of the area in the computing system is devoted to storing data and moving data. And not so much of the system is used for the computation itself, right? But still, the system is bottlenecked by memory, right? And this is a simplified representation, as you see, but if you look at the layout of many current computing systems, like, for example, this AMD CPU from 2020, you will see that most of the area is devoted to storing data. Like, observe, and in the whole chip, observe, for example, how much of the area is taken by the L3, only by the L3. We have L1 here, for example. We have L2 here, right? So it's even more than what is surrounded by the green box. Or if you take a look at this newer design from 2021, also from AMD, here they managed to increase, well, already in the left-hand side, top left, you can already see what's the size of the L3 cache compared to the rest of the system and compared to the cores. But even more recently, last year, they added a new layer of last level cache in order to make it larger from 32 megabytes to 96 megabytes, basically by placing another layer on top of the existing L3 cache in order to increase the size of the L3 cache, right, up to 96, as I said. So you see how much of the system is taken by the memory and storage. And here you have another example. This one is an IBM Power 10 from 2020. Observe also what's the size of the L3. It's 64 or 2 hemispheres of 64 megabytes, as you see. This is even more recent one, is Apple M1. If you look at the package, you'll find that well, there is a CPU containing a lot of SRAM, of course, like the last level cache, for example. But then we also have much more space being occupied by DRAM, right? And even more for the storage. Yes. Oh, the previous one. Yeah, so L1 is typically divided in CPUs, is typically divided in 2 parts. One is for instructions and the other one is for data. So that's basically why this is called D-cache. And probably if we could zoom in, we could see instruction, maybe it's here. I'm not so sure. No. This one is L1 D-cache. well, the instruction cache, L1I cache must be somewhere here as well. So maybe if you look for the picture and then zooming, you will find it. But yeah, that's basically the reason. Okay, good question. Okay, so yeah, as you see, well, we were here in this Apple M1, and as you see, most of the system is devoted to either memory or storage. Even if this memory is in the shape of a cache or register file, at the end is a lot of the system is devoted to storing data. So data overwhelms modern machines, and this leads to performance and energy bottlenecks. We will talk later about this work. It's this one here presented at ASPLOS 2018. But for now, let me show you this interesting number. Something that was measured in this paper is that 62.7% of the total system energy is spent on data movement. So imagine how critical this is and how important it is to figure out or find out ways of alleviating all this data movement. And one way of doing it is by creating intelligent architectures that can handle data well or data better than what they do. And what does it mean, handling data well? Well, first of all, ensure that data doesn't overwhelm the components via intelligent algorithms, intelligent architectures, or via the whole system with architecture, with algorithm, architecture, device, co-design. Take advantage of the vast amounts of data and metadata. Take advantage of them in order to make decisions, because if you know the data, you know as well what these data need to be processed. And based on that, we can make more intelligent decisions in computing systems. And finally, understand and exploit properties of different data in order to improve algorithms and architectures in various metrics. So some corollaries that we can find, based on the previous axiom in computing systems today is that these computing systems today are processor-centric instead of data-centric, which is more desirable to find out solutions for the data movement. They follow designer-dictated decisions instead of data-driven. Usually when the way that computing systems have been built is that the designer comes up with some heuristics to make the decisions based on what they expect that about the workloads and how the computing system should behave. And they design all these heuristics and these techniques to make decisions. But that doesn't seem to be the smartest way of doing so, right? Because applications may change a lot and different data might have completely different requirements, right? So that's why it makes more sense, or it would make more sense to make decisions based on understanding the data. And that's what we mean by data-driven. And related to this as well is that these decisions are based on the components, right? So why the system does this? Because the component has 2 different options or 3 different options or X if different options, right? But not options in the decisions that are related to the meaning of the data, right? So in the end, we need computing systems to be more data-centric, more data-driven, and more data-aware. And we need, and this way we will achieve, or we will end up designing more intelligent architectures and more intelligent computing systems. And that's this is a very recommended talk by Professor Mutlu, where he explains all these different points with much more detail. If you really want to create intelligent architectures and intelligent computing systems, then it makes sense to revisit the entire computing stack. And this is something that spans from the problem idea and the algorithm to the devices and the electrons themselves. And in the between, we have all these different layers: program, language, system software, the hardware-software interface, or the instruction set architecture, microarchitecture, logic, etc. So if we really want to create more intelligent systems, we will have to change all these different layers. So let's start talking about data-centric or memory-centric architectures. What are properties of data-centric or memory-centric architectures? First of all, process data where it makes sense or where the data resides. That's clearly very important, and it's the main topic in our lecture today. Second one, low latency and low energy data access. We should be able to access data in a more efficient manner, either from memory or from the storage as well. So we also want low-cost data storage and processing. And finally, more intelligent data management, right? Intelligent controllers that handle the data in a smarter way, and this way they provide robustness, security, and lower cost and higher performance. But today we are going to focus on this part here, process data where it resides or where it makes sense. And that's what, in general, we talk processing in memory or processing near data. It's also called, or you may find different names as well. We are going to talk about processing in memory, and we are going to discuss different categories or different classes of processing in memory that we can already find in research, but even in real products, in commercial products, it's possible to find them. So let's start with this part, processing data where it makes sense. Do you guys have any other question? Okay, so let's continue. What does it mean, processing where it makes sense? Processing where the data resides, or processing where the data is coming from, right? If you look again at this Apple M1 system, as I said earlier, most of the system is devoted to storing data or to moving data, and only a little bit of it is, only a little bit of the system is responsible for processing data, right? So the idea of processing data where it makes sense is processing data either when where the data is stored, might be storage, might be DRAM, or even where the data is generated. Because all these computing systems have sensors, right? And we could even process the data in the sensor itself and make the decisions there. That would save, for sure, a lot of time, because we don't need to bring data from the sensor to DRAM, or from the sensor even to storage, and then to DRAM, and then to SRAM, and then to the processor, the pipeline, right? So we can save a lot of time doing that, cycles, execution cycles, and we can save a lot of energy as well, because moving the data is very expensive in terms of energy. And I'm going to give you some examples later. This idea of processing where it makes sense or where the data resides is an old idea. It's not something that has started 2 years ago or 5 years ago. Back even in the 60s, right? There was some research on it. This is the oldest paper that we are aware of, this cellular logic in memory arrays, or this one from 1970, a logic in memory computer. By the way, this is a paper we have discussed here in this course in a previous edition, or even more recently, this is from the 90s. Back in the 90s, there was a lot of research in processing in memory as well, such as this, a case for intelligent RAM. Indeed, this is one of the papers that we will discuss in this course. Alexandra will present it, and we will discuss it in the course. But in memory computation or processing in memory seems to make more sense nowadays, and that's the reason why it's becoming a reality nowadays. The first reason is that there is a push from technology. The second reason is that there is a pull from applications and systems, and the designs, the processing in memory designs, are in the middle, right? From technology, what we see is that it was really necessary to make some changes and improvements to the memory system in order to make it more efficient. Why? Because for years it has shown, the memory system has shown scaling limitations. Memory technology scaling is not going well. And as you scale memory, more and more problems start to appear. And a good example of that is the RowHammer phenomenon. You might have heard of RowHammer. And so solving these scaling issues demands more intelligence in memory, right? Or designing more efficient and intelligent memories. And from applications, there is also a pull, right? And why is that? Because these applications are using more and more data. They need to process more and more data, as we have already mentioned. So this data access is the major system bottleneck. And the data movement is consuming a lot of energy and a lot of execution cycles. And so it's an issue with performance, it's an issue with energy, and it's an issue with sustainability. The idea is to try to find a way of fixing all of that at the same time, and by minimizing the data movement. And for sure, that can save a lot of energy and a lot of execution time. In terms of memory technology, we see that the industry, also academia, but industry is taking steps towards fixing the issue with memory scaling. And the hybrid memory cube was a good example at its time, designing a DRAM memory that is composed by multiple layers. At the bottom of it, we have a logic layer that has memory controllers, and this way we can access data with much higher bandwidth than in a conventional 2D memory. So using these 3D stack memories might be or can be a way of alleviating some of the scaling issues of memory. And an additional advantage of this 3D stack memory is that here in the logic layer, where, as I said, we have memory controllers, there is some extra area, right? Some extra area that we can use to embed some additional logic, some processing elements that can operate on the data that they have direct access to. So it's one of the enablers of processing in memory. Other examples of computing near where the data reside is this automata processing or automata processors from Micron. But even more recently, there are more specific processing in memory designs, such as the UpMem PIM architecture from 2019. And more recently, Samsung HBM PIM in 2021. Even more recently, this year, SK Hynix, they announced their processing in memory system. This is another one from Samsung, or this one is from Alibaba. We are going to talk briefly about this in the next slides. And there are many other designs. So these are, like, say, like the ones that are either commercially available already or have been prototyped and presented by the corresponding vendors. But there are many more, experimental chips and startups working on different techniques that we can consider processing in memory. These different ways of alleviating the data movement bottleneck and having more efficient systems. So if you want to recap on issues on memory scaling, this is a very interesting paper from Professor Mutlu that I would recommend you. And if you want like more specific examples on these memory scaling issues, then you should read about the RowHammer problem or the RowHammer phenomenon. You must have heard of it. The key problem with RowHammer, or this RowHammer problem, basically implies that there might happen bit flips inside memory when some other rows in memory are being accessed. If a particular row is accessed very frequently, and this row is open and closed multiple times in a short period of time, basically between memory refreshes, then there might appear bit flips in adjacent rows, right? And these bit flips, in the end, are errors, right? That may affect the reliability and the security of a system. You can read, I mean, in our group, there is a lot of research on RowHammer. This is also a very interesting paper, a retrospective on the work that was done back in 2014 and how the problem has evolved in more recent years. And Professor Mutlu has delivered and delivers different talks speaking about RowHammer. Indeed, I think he will talk next week about RowHammer in this course. So you will have the opportunity to learn much more, and also ask him about RowHammer and about other memory scaling issues. So we need to make memory more intelligent, and one of the things that we need to make memory more intelligent is to have more intelligent memory controllers as well. You can think about the potential solutions for RowHammer as an example of more intelligent memory controllers. Professor Mutlu will probably talk next week about BlockHammer. That is a proposal from our group. What BlockHammer does is using an intelligent memory controller to identify potential attacks, potential RowHammer attacks, to identify when a specific application is accessing repeatedly, very frequently, the same DRAM rows. If that happens, an intelligent memory controller should be able to figure out, right, and make some actions or take some actions in order to avoid the RowHammer attack, right? Like, for example, throttling the accesses from this suspicious application, let's say. And intelligent memory controllers can also be useful with not only DRAM, but also emerging memory technologies. For example, phase change memory. You can have an intelligent memory controller that decides what's the right place in a system where you have a hybrid memory system with, for example, DRAM and PCM. An intelligent memory controller is able to make decisions on where is the right place, either DRAM or PCM, to place, to store a specific data, depending on what are the needs of that data. So remember that it's important to understand the data well and build the system around the information that we can get from the data, right? And this way we can solve many of the issues in current computing systems. So we need intelligent memory controllers, and this can avoid many failures and enable better scaling. So three key systems and application trends. First of all, data access is the major bottleneck, and applications are increasingly data hungry. Second one, energy consumption is a key limiter. And third one, data movement energy dominates compute. And this is especially true for off-chip to on-chip movement. I mean, also inside the chips, there is a lot of data movement, right? But because it's on chip, it's usually less expensive than going off-chip. And this is in the end the future that we are looking for, right? If we enable more efficient computing systems that save energy, we will also build computing systems that are more sustainable, and hopefully we can have or we can continue having these nice and beautiful landscapes instead of something ugly and dirty like this, right? So it's one of the key goals of building more intelligent systems and building systems that are more data-aware, data-centric, and data-driven. So we have an opportunity, and we'll have a challenge and also an opportunity for the future, that is building computing systems that are higher performance, more energy efficient, and more sustainable, and all of that at the same time. Remember that the problem is accessing data is the major performance and energy bottleneck, and this happens because our current design principles are a great energy waste, or cause a great energy waste and performance loss. Basically because data is stored here, computing is done here, and in between the only thing that we have is a very thin funnel, right? That avoids not avoids, but impedes in some way the data movement between one side and the other side. So this happens because processing of data is performed far away from the data. Remember, in the von Neumann model, that computing is done on the left-hand side, while memory and storage, data is stored in memory and in storage on the right-hand side. So this comes at a great system cost, and it's something that has been discussed and identified or diagnosed long time ago. From this interview with Richard Seitz in 1996, he said, or the title of this interview was, "It's the memory, is stupid." And back then, Richard Seitz was working with others on designing a new processor. And one thing that they realized is that all bottlenecks or all key bottlenecks in the system were coming from accessing data, right? And one thing that he could foresee back then is that the problem was only going to become even worse, right? And that was 1996. But few years later, and 7 years later, concretely, we already observed that. This is from Professor Mutlu's PhD thesis. One thing he observed when motivating the work for this run-ahead execution was that most of the execution cycles were spent on accessing data from the DRAM, from the external memory. Right? That's why all this fraction of the execution time, more than 55%, was spent on L2 misses. Right? And this is the paper, the run-ahead execution from 2003. But from 2003 until now, things have not gone better, right? And this is from a 2015 paper from Google, where they analyze all their data center or important data center workloads that they use in their data centers, right? And one thing that they observe is that most of the execution cycles are spent on accessing data. In particular, in this slide, what we can see are the results for what is called the top-down performance analysis. In the top-down performance analysis, we have different levels in the analysis, but let's say in the upper level, we have 4 different categories, and these categories represent how the execution cycles are being spent. You know that CPUs are composed, they have a pipeline, right? And this pipeline has multiple stages, and in each of the stages, we have one instruction, typically, or hopefully, the entire pipeline will be occupied with different instructions being executed at different stages, right? Like, first of all, fetch the instruction from memory, then decode the instruction, then access the register file, etc., right? But sometimes you have to wait for data, right? For example, you have to wait for data to come from the off-chip memory, from DRAM. And what that means is that some instructions will have to be stalled. And if they are stalled, then there are some cycles in the pipeline that we are not using, right? Some of the stages will be empty, won't have any meaningful instruction for some of the cycles, right? And that happens a lot in CPUs. Indeed, the green part is like the, let's say, like the good use of the CPU. That means retiring means that we are really using those cycles in a productive manner. We are really executing instructions. The rest of the time, instructions are waiting, either the front end, or they have to, for example, repeat execution of some parts of or some instructions due to bad speculation, for example, a branch misprediction. And most of the time is spent on this backend bound section. Backend bound section might be related to execution units, but most of the times, in most of the cases, this backend bound section or these backend bound cycles are being spent on accessing data, either from caches or from the external memory. So as you see, the problem is not better these days, it might be even worse. And that's, if we look at the execution cycles, if we think about the energy that is spent, it might look even worse, I would say. You can compare in this slide from Bill Daly, he presented in HighPeak 2015, you can compare the total energy that is typically spent on accessing one cache line from memory. We're talking about the order of nanojoules, while computing double precision addition, for example, is in the order of picojoules, right? So we have the situation that the memory access consumes something between 100 and 1,000 times the energy of a complex addition. And we say it's complex because it's double precision, right? And here you have more related data. This is from another paper from 2016. What you can see here is like what's the energy for a 32-bit operation. This operation might be an integer addition, floating point addition, an access to the register file, a multiplication, either for integers or floating point values, an SRAM cache access, and a DRAM access. And you can see what's a huge difference that exists between computing or even accessing data if it's on chip, right? Because the SRAM cache is on chip, same as the register file, and compare it to accessing data off chip, right? So it's much more energy accessing data off chip. We are talking about 6,400 times more energy for a memory access than a simple integer addition. And back to, I mean, and all of this results in, when you go to the observing what's the total system energy consumed by a complete application, ends up being 62.7%. So a lot, right? And this is, by the way, another paper that we will discuss. And I think this is indeed happening in the first session, right? So I hope we will also have a good discussion about this paper. So in the end, we do not want to move data because it consumes a lot of energy, and the way of doing it is doing a paradigm shift, shifting to a new paradigm that can be called memory-centric computing, can be called processing in memory, but essentially is a paradigm shift to enabling computation with minimal data movement, computing where it makes sense or where the data resides. If the data is already in the register file or in the L1 cache, it makes no sense to compute in memory, right? Because the data is already near the processor. But in most of the cases, that's not going to happen. In most of the cases, we have to go to the main memory, to the external off-chip memory. And in the end, the goal here is to make computing architectures more data-centric. The basic idea of processing inside the memory or processing in memory is pretty simple, right? On the left-hand side, I have the processor with its own on-chip memories, like the cache. On the right-hand side, I have the off-chip memory. The basic idea in processing inside the memory is still compute still execute most of the program in the processor core, but at some point, specifically for certain applications or certain operations that can benefit from this, we offload the computation to the memory side, assuming that we have some sort of compute capability there. And we are going to see later what are the different possibilities that we have for this compute capability. But after offloading some computation, for example, a database query, this orange compute capability that we have here on the right will access memory, will perform some computation, and then return the results to the CPU. So as you see, it's conceptually simple, but it's not so easy to implement in real systems. Why is that? Because there are many open questions. For example, how do we need to design the memory, or how do we need to design the processing engines or processing elements that we have there, and how should the controllers be, right? Remember that we talk about intelligent memory controllers. These memory controllers, for example, can help on deciding when to offload something to memory or when to not offload something to memory because maybe the data is in the cache. Or maybe because you will bring the data from memory to the processor and then you're going to reuse it a lot. In those cases, probably also doesn't make sense to offload the computation to the memory, right? Because the processor is faster than any sort of processor that we can have in the memory side. So we have to decide as well how to design these processors and communication units, what should be software and hardware interfaces, basically how users can make use of these new capabilities, how do they need to write their new software, or for example, how the ISA needs to be modified or needs to be enhanced, right, or extended. It's also necessary to change system software. The OS will have a lot of responsibilities here in data-centric computing systems, same as compilers, languages, etc., or even the algorithms themselves and the theoretical foundations might need to be rethought, right? If you have some new compute capability in your system. And all of this spans the whole stack. So if you want a quick review on processing in memory works and what are the open problems, I can recommend you this book chapter, A Modern Primer on Processing in Memory. So in the end, we need a paradigm shift and we need to think differently from past approaches. And there are different ways of doing that, right? We are going to see next a few examples of what we call processing in memory, and we are going to start with a general classification of what is processing in memory. Typically, we distinguish between two main classes of processing in memory. The first one is called processing near memory. As the name says, you're going to process near where the data is stored, but not exactly inside the memory itself, but near the DRAM bank, for example, or near the memory subarray, for example. While in the other possibility, we process using the memory. So here, as we will see in some good examples, we are going to take advantage of the operation of memory itself, of how memory works. Right? We are going to focus today on DRAM, but these processing using memory techniques are applicable to other memory technologies as well. So if you check the book chapter, you will see that there in section 5.2, we talk about the two approaches, processing using memory and processing near memory, and you will find this table one with different examples of enabling technologies. Processing using memory is possible these days in SRAM, in DRAM, and also in non-volatile memories like PCM, MRAM, ReRAM, and memory stores, etc. We are going to focus today on DRAM. And in the lower part of the table, what you have is examples of near memory processing. I have already mentioned some of these, like, for example, logic layers in 3D stack memories. Remember this slide with HMC. There is a 3D stack memory with multiple layers of DRAM, and at the bottom we have a logic layer. We could have a small processor or a small accelerator in this logic layer. But there are many other examples, right? Like silicon interposers that are used, for example, with HBM memory, another 3D stack memory, high bandwidth memory that is being used in FPGAs and it's being used in GPUs these days. We can also have logic memory controllers or in the memory chips themselves, the AppMem example, the AppMem architecture that we are going to use as an example today, computes near the banks. Or we can have logic in memory modules. We are going to very briefly mention one example of these, and also, near the caches in other places of the memory hierarchy as well. Go ahead.
Sensors, you reuse these methods for processing their sensors?
In some way you can, right? So processing, I mean, it's very similar as well. So instead of computing where the data is stored, you're going to compute where the data is generated. It will depend on the sensor. It will depend on how large the sensor is, on how much compute capability you could have there. But if you have a sensor, probably this sensor will have to send data to some central processing unit, a CPU, for example, and this sensor before sending the data will have to store it somewhere, right? Maybe an SRAM or maybe a small DRAM. So you could have processing in memory near the sensor as well, or inside the sensor as well. Okay. Let's go ahead with the two approaches to processing in memory. The first of them is processing near memory. So in processing near memory, well, first of all, from now on, you should see memory as an accelerator, right? And in processing near memory, here we have the memory, and near the memory, we have some specialized compute capability in memory, right? Imagine that this is a small CPU, or it might be a specialized accelerator, for example, for neural networks or for genomics workloads, right? So we are going to see how I mean, we are going to see how these systems can be built, but that's the thing, right? So you can see memory now similar to a conventional accelerator. And in order to start with a pretty good example, we are going to start talking about, one class of workloads that is prime example of workloads that can benefit from processing in memory. And these workloads are graph processing, and graphs are being used everywhere these days. The slide is a little bit outdated, as you can see, but basically reflects that there are very large graphs out there, and these large graphs are used for many different applications. And here you see some examples from Wikipedia, Facebook, Twitter, Instagram. These graphs, for example, if it's a social network, they will represent how users are connected, right? And based on that, if you analyze that information in the graph, you can figure out things about the users that might be useful for someone, right? But if you want to process these large graphs, then you need very powerful systems, right? You can decide to use a multi-core CPU or a multiprocessor. The problem is that even if you increase the amount of compute power that your system has, you may not see so much performance improvement. And I think that this is very clear motivational data. For 32 cores, you get certain performance. For four times more cores, 128 cores, you get only 42% more performance. So for 4 times more cores, only 42% improvement. So it really doesn't make sense. And what's the reason for that? The reason is accessing data. The reason is that the memory bandwidth is fully saturated when trying to process these very large graphs. And even if we use more cores for this task, we cannot increase the performance significantly. And basic or key reason is the algorithms themselves. Graph processing algorithms usually have very little amount of computation. This example is PageRank. As you see, the only thing that we have to do is performing one multiplication and then one addition in each iteration of this for loop. And also another problem is that there are frequent random memory accesses. And what that means, and that happens because of the graphs themselves, right? Graphs themselves are very sparse. You, as a user of a social network, are connected with certain people, but the person next to you might be connected to completely different people, right? Maybe you share some common contacts or friends or followers, but maybe as well, most of them will be completely different. So it's a lot of information there, but this information is very irregular. And if that happens, then your accesses to data will be irregular as well, and they will be basically random. What's the problem with random accesses? You have to go to memory, you bring one cache line, this cache line is 64 bytes, but then you may only use a small amount of those 64 bytes. Maybe you only use 4 bytes because you just need an integer like the age of one person, or maybe it's I don't know, it's a floating point number because it gives you the height of this person or whatever. But in the end, you are reading or bringing a lot of data from the main memory to the processor, and only a little amount of this data is being used. And if you store this data in the cache, you may be able to reuse it later. But look at the algorithm itself. It's iterative, right? And in each iteration, it goes over all vertices, over all nodes, and it goes over all neighbors, right? So if the graph is huge, let's say gigabytes or even more, terabytes, then it won't fit in the cache. And if it doesn't fit in the cache, every time that you want to check the age of this person or the height of this person, you will have to go to memory, right? And when you bring the data, only very little amount of computation. So that's why it's inefficient, and that's why the memory system is overwhelmed, and that's why we don't see much performance improvement when we increase the number of processing elements or number of cores. So the opportunity here is to make use of processing in memory capabilities in some way, such as, for example, 3D stack memories, in order to perform some of the computations near the memory and fixing this problem of having to bring the whole cache line from here to the processor just for very little amount of computation, right? The Tesseract system is a coarse-grained accelerator processing in memory-based accelerator for graph processing. And what it proposes is an accelerator, as you see, is composed by many of these 3D stack cubes, as you see. They are connected with each other. The entire graph, imagine a huge graph of gigabytes or terabytes, is mapped onto these different cubes, onto these different cubes of 3D stack memory. And then inside each of the cubes in the logic layer, we will have some compute capabilities. Tesseract in particular proposes to create this sort of many core processor inside the logic layer. And this whole processor is composed by many in-order cores. As you see, they are very simple cores, but they are able to do the computation that is needed for these applications, for this graph processing application, right? So yeah, you can see this as a GPU, for example, is a coarse-grained external accelerator. It's not a pure extension of the CPU. It's just an accelerator that sits near the CPU, maybe connected through the PCI Express bus, same as a GPU, for example, but is specialized for certain workloads that have certain issues, like graph processing, as we have explained earlier. And accessing data here is in the in the center of the design. This design considers, for example, the use of communication via remote function calls. They have a message queues here such that one specific core may receive instructions, may receive commands from another core because it wants to surrogate some of the computation to the other core. Why is that? Because probably the data that this core needs is closer to this processor. And if it's closer, because it's on top of it in one of these memory layers, in one of these DRAM layers, then it will compute faster. So that's why it makes sense to create the system around the data itself, around the computation that needs to happen and the data movement that needs to happen. In some cases, Tesseract proposes to offload or the computation to another core. In other cases, it also makes use of techniques like prefetching in order to bring data from some other part of the system to the specific core, because in that case, it's more efficient to do so. I'm going to show you some performance results for evaluated systems. This is, in the paper, they compare, conventional processor-centric systems like this one composed of out-of-order processors, either with DDR3 memory or with HMC memory. This is another baseline. In this case, it's not out-of-order processors, but in-order processors, many more, right? But all of them accessing external memory, HMC in this case, and they compare to Tesseract, right? You can already see what's a key advantage of Tesseract. Key advantage of Tesseract is that the overall or the aggregated bandwidth of the whole system is much larger than in any of the other combinations, right? And there is where the main benefit is going to come from. It translates into very good performance improvements. We are talking about almost 14 times faster execution on the Tesseract system, and a great energy reduction, 8 times less energy consumption in this case. And this is the paper presented at ISCA 2015. I would consider this one like a prime example of recent research in processing in memory, and this work has influenced a lot of later research as well. In this direction of coarse grain accelerators, this is another good example. GenStore, in this case, it's not in memory, it's in storage processing. So in this case, the accelerator is near the storage, right? In an SSD device, for example, you can also have some compute capability and accelerate some workloads. In this case, genome sequence alignment. In genome sequence alignment, as you know, you usually need to use huge data sets that are the reference genome, for example, might be from different species as well, and all of that. In the end, I mean, all of that is stored in storage. And if you want to process, first thing you'll have to do is bringing everything to the memory, right? And that's super costly. If you do it direct, or you at least do some of the computation directly in the storage, you will save a lot of data movement to the memory and to the processor. Processing in memory is becoming real. These previous two works are examples of research, academic research, but processing in memory is becoming real. After years and years of academic research and also researching industry, we start to see the first processing in memory systems. And this is the first one to appear, and the first one to become commercially available is the UpMem pin system processing in DRAM engine that basically consists of the DDR4 DIMMs with multiple chips, and inside the chips we have not only memory arrays but also small processors called DRAM processing units or DPUs. Near each bank we have one of these small processors. You cannot see anything in this picture except the DIMM itself. You have to believe that inside each of these chips there are 8 memory banks and also 8 processors, or 8 of these DPUs, and here you have some sample frequencies at which these DPUs run. As you see, not so fast as a CPU or a GPU, but it's still pretty much capable. We have worked with this UpMem PIM architecture for some time already, and this is one of the systems that we have access to. Is as you see, it's a dual socket CPU and connected to the memory channels. There are DRAM DIMMs because the system still contains, let's say, traditional or standard main memory. And then we also have these PIM-enabled DIMMs that are the UpMem DIMMs themselves that are here represented, right? So whenever we want to compute something using the PIM-enabled memory, the CPU will move data from the DRAM to the PIM-enabled memory, then we'll compute here for some time, and then we'll retrieve results from the PIM-enabled memory back to the DRAM, right? And that's how these systems work. You can learn more in some of the talks and lectures that we have delivered about this system. This is one example one. And now, well, what I want to do is just introducing briefly what these DPUs are. They are simple processors, very simple processors. The figure is incomplete, but the memory bank is right here on the right-hand side, right? The processor, this small core, this DPU, can access data that resides here in the DRAM bank, right? And the way of accessing data in the DRAM bank is, first of all, asking this DMA engine to move data from the DRAM to this WRAM, that is a sort of a cache, but it's not really a cache because it's not hardware managed. It's managed by the programmer. So the programmer has to tell the DMA engine when to bring data from the DRAM to the WRAM, and then this pipeline will access instructions from the instruction RAM and operands from WRAM and will perform the operations that are needed, right? The key advantage of this approach is that we are very close to the memory. And not only that, is also that we have one of these pipelines, one of these cores, every DRAM bank. In one chip, we have 8 DRAM banks, but in one DIMM, we have 16 chips, and in the system, we can have up to 20 DIMMs. So you calculate, this gives you 2,560 of these processors and these memory banks, right? So that can be very, very efficient. If you take a closer look at the pipeline, it's an in-order pipeline, it's fine-grained multi-threaded. This means that up to, well, in this case, up to 24 threads can run. And what the pipeline basically do is that in the very beginning, in the dispatch stage, selects one thread, goes to memory, brings the next instruction that needs to be executed by this thread, and then starts executing it over the pipeline stages. Next cycle, next thread, next instruction, and so on, right? And that's basically how the fine-grained multi-thread architecture works. We did a lot of analysis and characterization of this architecture, and one thing that we noticed is that you need to use at least 11 threads in order to achieve the peak throughput of this system. That's why you see that the performance or the throughput for all these arithmetic operations saturates at 11 tasklets. But we can also observe that there is a lot of difference between the arithmetic throughput of different operations, right? So if you observe integers with respect to double precision, or even addition and subtraction compared to multiplication and division, we see that the throughput is completely different. And that's because of the instructions that are natively supported by the hardware. It's a very little processor with a very simple pipeline with low speed, and with limited support to different instructions and operations, right? That's why multiplication and division and floating point operations are way slower than addition and subtraction of integers that are natively supported. Is this an issue? Yes, this might be an issue for some workloads, right? So for example, if you want to do many multiplications as are needed, for example, in dense matrix or sparse matrix computations, you may have issues, right? Especially if you work with floating point values, but the architecture is not designed for floating point. Maybe in the future, there will be a much more capable version for floating point. And don't forget that this is the first commercially available PIM architecture, right? So hopefully things will improve fast at some point when the PIM architectures become much more available, right? And much more ubiquitous in computing systems. We also characterize what's the bandwidth that the DPU can enjoy from the access to this DRAM memory, and to do so, we use the stream benchmark, that is a typical micro benchmark to characterize bandwidth. And there are different versions of the stream bandwidth. One thing that we can observe is that for a single DPU, the bandwidth is more than 600 megabytes per second. Now multiply that by 2,500, and then you will get much higher value, nearly 2 terabytes per second. That is a lot in reality, right? Especially for DDR memories. If you compare it to HBM2 or HBM3, it might not be that much, but HBM memories are way more expensive than DDR memories, right? So it's pretty good. One thing that we can also observe is that the saturation point for the bandwidth for some of these micro benchmarks is less than 11. Remember that in the previous slide, we said that saturation point happened at 11, but here it only happens at 11 for 2 of the workloads. And these 2 of the workloads are Scale and Triad that have only a little bit more computation than the other ones. A scale is just a multiplication, triad is a multiplication and an addition, compared to add, for example, that simply does 1 addition per element that is accessed from memory. But we already see different behaviors. And key takeaway here is that saturation point at 11 tasklets is happening with very little computation, right? So we expect that when we have more computation, it will continue happening. And that's because most of the execution cycles are spent on the pipeline, on executing instructions, not accessing memory, right? So here it happens exactly the other way around as it happens in conventional processors. So this workload is compute bound, these 2 are compute bound, and we expect that most real workloads are going to be compute bound in this architecture. So we have solved one problem that was access to data, right? Now we have another problem, that is that the processor is not that fast. But that might still be good for many important workloads. You can read the whole analysis in our paper. This is another version of the paper that got published at a journal. There are several talks that we have delivered, so there is much more information about this. And here you can just get some key takeaways. This relates to what I was saying earlier, that the PIM architecture, this UpMem PIM architecture is fundamentally compute bound, basically because if we analyze, the arithmetic throughput versus the operational intensity, we observe that the saturation point happens at very low operational intensity. So as soon as we are doing something like one integer addition per every 32-bit element that we read from memory, we are already in the compute bound area. So that's where we have the bottleneck in this system, in the computation itself, the execution of instructions, which, by the way, has one advantage. If I know that the problem with my system is the number of instructions I execute, what I should try to do is reducing the number of instructions that I execute. If you try that in a CPU or in a GPU, not always executing less instructions translates into performance improvement, especially if the workload is bottlenecked by the memory access, right? But here, we got rid of that problem. Now the problem is a different one, is that we want to write programs that are more efficient and execute a lower number of instructions. We also evaluated this with real workloads and compared to CPUs and GPUs. So blue bar is CPU, green bar is GPU. The other two are two different PIM systems. As you see, there are some workloads for which the PIM systems are faster, while for others, they are slower than the GPU. Indeed, here the classification is done compared to the GPU. The workloads that are most well-suited, so these ones here, use no arithmetic operations or only simple operations. Remember that multiplication, division, floating point calculations are very costly in this architecture, but if your workload is just using addition and subtraction, then you are perfectly fine. You will be faster than the GPU in this part here. Also, they require little or no communication across DPUs. This is something that I didn't mention earlier, but all these different DPUs, these different in-order processors work completely independent to others. So if they want to communicate, then you'll have to move the data from the DPU to the CPU and then from the CPU to another DPU. So in the end, you will be falling into the data movement bottleneck as usual. So ideally, an application that will benefit from this system won't use much communication across DPUs. And finally, you can see some more exact numbers about the comparison to CPUs and GPUs. For CPUs, for example, the UpMem system was, or the UpMem systems were like faster than the CPU for 13 of the 16 workloads that we evaluated, and for 10, and compared to the GPUs for 10 of the 16 workloads, right? So there is some promise here for sure. And yeah, you can find many more details in the paper. This is a shorter version of the paper, and this is the whole list of workloads that we evaluated. We call this collection of workloads PRIM benchmarks. PRIM comes from processing in memory, as you can imagine. And as you see, the workloads are from different fields like linear algebra, sparse and dense, databases, data analytics, etc. All the code is available, so if you eventually have access to a processing in memory system and can play with this, you can access our code. Is open source. Here you can find the paper, and this is also another paper that we will discuss in this course. Actually, will be, I think, the last session of the semester. And yeah, as I said earlier as well, if you want to learn more, there are a lot of talks that we have delivered. And we continued working with this processing in memory system. This is an example machine learning training on this processing in memory system. These are some key takeaways that we obtained from our analysis of machine learning workloads in processing in memory systems. In the end, these takeaways are pretty much in line with the takeaways from the previous work. For example, lookup tables can be pretty useful to accelerate certain operations, complex functions like sigmoid, for example, that requires exponentiation. If you try to do that with the ALUs that the system has, it will take many, many cycles because you will need to do function approximation because there is no native hardware to support sigmoid. But if you can somehow create a lookup table where you can access for whatever value you need to calculate the sigmoid, you go to the lookup table and fetch the result directly because you are now very close to memory, then it will be much faster, right? So yeah, these are some of the key takeaways for this work, machine learning training on a real processing in memory system. And it's not the only thing. Sparse matrix vector multiplication, which you may know is very much used in, it's a key primitive in many, many applications. It's something that we have also experimented with in these real processing in memory systems. And it's also something that was published this year, and there are as well available code and available lectures and talks if you are interested in this. And here, a couple of slides about this sparse matrix vector multiplication on real processing in memory architectures. We did a very wide analysis and evaluation of SPMB on this architecture, creating up to 25 kernels with different compression formats. You may know that sparse matrices can be compressed in multiple different ways. CSR is the most typical one, but there are other formats as well. Data types, data partitioning strategies, synchronization strategies, load balancing strategies, and in total, as you see, 25 different implementations. Evaluation with different sparse matrices from well-known repositories and comparison to CPU, GPU, and recommendations for the future as well. And this is the one of the talks that I mentioned earlier. But the UpMem system, as you already know, is not the only real-world processing in memory system. Last year in 2021, Samsung announced their processing in memory system based on HBM memory. It's a 3D stack memory, similar to HMC. But in this particular proposal, instead of placing the compute elements here in the logic layer, as I explained for is typical in Tesseract, for example, here is where we have the compute units. Samsung folks, what they did was something different. They modified some of the DRAM layers in order to embed processing engines inside those DRAM layers. And those processing elements are something like this. They are called programmable compute units. And they are relatively simple. One of the reasons for that is that they are specialized for certain type of applications, artificial intelligence, neural networks. And for these applications, what you need a lot is computation with matrices, matrix multiplication or matrix vector multiplication, right? So if you need to do that, multipliers and others is what you need. And if you are operating on many data at the same time, you're operating on entire matrices at the same time, you can perform many dot products at the same time, many multiplications, many additions at the same time. That's why, because there is a lot of regular data parallelism there, that's why it makes sense to use SIMD units. That's why you can see here other times 16 multiplier times 16, because these are SIMD units with 16 lanes. So you can operate on 60 elements at the same time. And this is sort of the pipeline, starting from the decoder, multiplier, other, and then controller to access the register file, either to read instructions or to read and write operands or data. And this is the reduced instruction set, because you need what you need, right? Depending on, but that's why it's important to understand the data and understand the applications and the algorithms as well. What are the important algorithms for Samsung folks? Neural networks, and artificial intelligence, machine learning. What do I need for them? Multiplication, multiplication and accumulation, multiplication and addition, or simply addition. There you have your instructions, right? The instructions that you need. You don't need much more complex pipeline and much more complex instruction set if you are targeting very specific applications. And here you see, a view of the layout of one of the DRAM layers. Near every two DRAM banks, we have one of these PCU blocks, and the PCU block can sustain accesses to this bank and this bank, as well as the internal registers that it has and you have seen in the previous slides. This is the other proposal from Samsung. This is on the DIMM, right? This is computation on the memory module. They extend this buffer here in order to have some sort of compute capability. In particular, in this paper, what they used is this experimental platform where in a couple of these DIMMs, they have an FPGA. On top of the, on the DIMM, they have an FPGA. And this FPGA has direct access to the 2 memory ranks that you can see there. And this way accelerate some particular workloads, right? In particular, they use a deep learning recommendation system, or one stage of this deep learning recommendation system, not the whole thing is executed here. Maybe, yeah, part of the system is still being executed in the CPU. And this is the announcement that SK Hynix made this year in February 2022. Their aim or accelerator in memory architecture is somehow similar to the first proposal from Samsung. As you see, there are also, these DRAM banks, and near each of the banks, there is one PU, processing unit, or process unit. I'm saying that it's kind of similar because of the applications that they are targeting. In the end, they are also focusing on the same type of applications, and that's why they have, in each PU is basically a multiplier, 16 times multiplier, so it's a SIMD multiplier with SIMD lanes, and then there is this other tree in order to perform reductions, in order to perform additions, because that's basically what you need when you're doing a matrix multiplication or a matrix vector multiplication. It's a dot product where you first multiply and accumulate, and that's what you can do using these PUs here. There is something I like from this proposal is that they also figure out a way of evaluating or executing activation functions in a fast and efficient way, and they do it in a similar way as we did it with the AppMem architecture for sigmoid that I just mentioned a few slides ago. Is by using a lookup table in some of these DRAM cells, in some of these rows in each memory bank, and then they also have an interpolation function, an interpolation unit, in order to be more precise in the calculation of the activation function. Another interesting thing they have is this supplementary SRAM buffer that is used to move data around. You can move data from one bank to another bank by placing the data first in this GB and then from the GB to another place. I'm mentioning this right now because this resembles some of the techniques that I will mention later in processing using memory that allow us to move data inside memory without having to move the data from outside of the memory, or to outside of the memory. But yeah, we will see that in a few slides. This is another recent proposal. This one is for from Alibaba, and it's for a recommendation system. So it's even more specialized. As you see, they have these neural and match engine that are for, like 3 specific steps in the recommendation system. So it's more specialized, but as you see, it's basically the same idea, right? You have memory on one layer, and then you have another layer where you have the compute elements. So this is processing in memory in the real world, and it's something that we cover in our courses. For example, in this PIM course that we offer every semester, and here you have links to the Spring 2022 edition. There are lectures about the AppMem architecture, Samsung proposals, Alibaba, SK Hynix, etc., and then even more, right? Like more, and the last lectures are about more, academic research proposals from our group. Okay, any questions about processing near memory? Everything super clear. Okay. Let me very briefly, because we don't have so much time, but quickly go over the other type of approach, all right? Processing using memory. Still, we see memory as a conventional accelerator, but now computation is not being done here in a separate unit near the memory. No, now computation is going to be done with the memory itself, and that's what makes it even fancier. The first application that we target here, or the first use case that we target here, is data copy and initialization. Why is that? First of all, because it's simple. Second, because it's used everywhere, right? You may find it in your own programs because you need to initialize one memory array full of zeros, for example, or because you want to main copy from here to there. But then it also appears in many operations in the system, like the typical, checkpointing, page migration, cloning, and the duplication, etc. Even from this paper from Google that I mentioned earlier from 2015, they measured that 5% of the total execution cycles in Google Data Center are spent on data movement, right? On even either mem move or mem copy. So 5% might not look that much, right? But if you have a huge data center, then that for sure will be a lot of energy that you are spending on in these 5%, right? And the problem is that if you want to, here I have a simplified slide. So the problem with memory copy is that if you want to copy from here to here, first of all, you have to bring this whole part of the memory, this, say, DRAM row, for example, all its contents, maybe 8 kilobytes or something like that. You have to bring them all cache line by cache line to here. And if you want to write here, you will also have to bring these cache lines from here to here and then perform the copy here, right? And then move the data back to memory. So that's a lot of waste in time and a lot of waste in energy, right? Ideally, we can do something like this. We can directly copy inside the memory without having to go out of the memory. And this is going to be low latency. It's low bandwidth utilization because we don't need to use the memory channel, and it doesn't pollute the caches as well, right? We are not bringing data for nothing, for no reuse, because there will be no reuse after we perform the copy. So we can save a lot of data movement if we have this in-memory copy capability, right? And as you see, we can as well reduce a lot the latency and reduce a lot the energy consumption. And that's something that can be done with row clone, a technique that was proposed by our group in 2013. Basically, row clone proposes to open a row that is a source row, activate this row. That means transferring the contents of the row to the local row buffer. In this example is 4 kilobytes, as you see, and then open a destination row, activate the destination row, and directly transfer this row from the row buffer to the destination row. If you do that, you can, with these two consecutive activates at negligible hardware costs, you can be much, much faster when performing operations like memory copy or initialization. And that's what you can see here if you compare the baseline that is using the CPU compared to the technique that I just explained. You can save more than 11 times the latency and save 74 times the energy, right? These are other techniques that the same paper proposes. This one, for example, the green one, the interbank one, would be similar to it's indeed pretty similar to the one I mentioned in the SK Hynix chip to copy data from one bank to another bank. As you see, they are still more efficient than doing it through the CPU, but not as efficient as doing it inside the DRAM subarray itself. You can find all the details in the paper. And what is interesting is that even though existing or current DRAM chips are not designed to support this operation, there are people who have tried to support this operation by using experimental memory controllers, like a soft NC memory controller from our group. And the Compute DRAM work presented in 2019, they indeed were able to execute row clone operations with real chip, with off-the-shelf DRAM chips that are not designed to support this operation, but by playing with the timing parameters of DRAM, they were able to emulate these row clone copies. You will learn more for sure about row clone and about compute DRAM in this course, because this is also another paper that we are going to discuss in the course. Using the insights from the compute DRAM paper, we developed sort of an end-to-end framework to go even farther in the studies related to processing in memory and processing in DRAM, because in the end, if you just show that in the chip it's possible to use something like row clone, then that's fine. But it's going to be much more complex to integrate this operation, this row-to-row copy in a real system if you don't have enough support. And in order to develop this support, it's necessary and it's good to have experimental platforms. And this is one experimental platform that we propose. This is the PyDRAM framework, where you see inside an FPGA board, it's possible to design and implement a RISC-V core. And this RISC-V core in the FPGA accesses an external DIMM, and this DIMM might be, off-the-shelf DRAM DIMM, but by using the ideas explored in compute DRAM, it's possible for this RISC-V core to take advantage of row clone operations inside this memory. So that's the basic idea. PyDRAM is also publicly available, is open source, anyone can download and implement in their FPGA. And for row clone, for example, one thing that we obtain are pretty interesting performance results for copy and initialization, as you see. So this is the throughput improvement if you compare doing this copy and initialization using the RISC-V core or doing it directly inside the DRAM chip. As I said, PyDRAM is open source, and this is another link to an extended version that is on archive. And also there are talks available. For example, this lecture that Ataberg, who is the main author, the first author of the PyDRAM, he delivered in our processing in memory course. Okay, row clone, research, because row clone is exciting, right? You can save a lot of energy and a lot of execution cycles by directly copying from row to row. So there have been improvements on row clone. First of them is LISA, a way of doing inter-subarray copy in a faster manner as the way that the row clone paper proposes. But then there are other ways, like, for example, Figaro can also do internal data movement using the global row buffer, but in this case, at a much finer granularity. Instead of copying entire rows, you're copying pieces of 64 bits. Or, for example, this NOM network of memory for interbank copy using a network in 3D stack memories with a logic layer. So this is the LISA paper. Very, very briefly, what the LISA paper proposes in order to copy data from subarray to subarray inside the same DRAM bank, what they propose is to include some isolation transistors that connect bit lines in subarray 1 to bit lines in subarray 2, depending on whether these isolation transistors are active or not. We will be able to move data from one subarray to the other subarray, and that has different applications. For example, fast bulk data copy that is not as fast as copying inside the same subarray with row clone, but is way faster than doing it through the CPU. And here you can see also some summary of results for other applications of this technique. This is the paper. This is a link to the other paper, Figaro, also data movement at a much finer granularity, and also this network of memory. The good thing of doing these copies inside memory is that you can continue using your imagination to figure out new ways of operating inside DRAM, right? And that's what the authors of the Ambit paper did when they came up with an interesting idea of activating 3 rows at the same time. Imagine that this is one bit line. It has multiple rows. These are 3 of the rows or 3 of the cells, A, B, and C, connected to the same bit line. Normally in DRAM, when we want to read or write, what we do is activating only one of these, for example, C or A or B, right? But what happens if you activate 3 of them at the same time? If you activate 3 of them at the same time, they will do what DRAM cells do when you activate the access transistors. That is, they start leaking their charge onto the bit line, and that causes a voltage deviation, a voltage perturbation, this delta that you see there, and at some point you enable the sense amplifier. So the sense amplifier amplifies the perturbation in the bit line, and this is the value that you read, right, from the DRAM cell. But if you have 3 at the same time, the sense amplifier is going to amplify the perturbation here. But this perturbation is what? It's caused by the 3 cells at the same time. If you remember, 2 of the cells were charged, 1 of the cells was discharged. What happens here? What do you think that happens? When the sense amplifier is enabled, what happens is that it wins the majority, right? There were 2 full charge, 1 fully discharged. When you activate the sense amplifier, the 2 that correspond to the majority win. And in the end, what you have here is a majority function. And this is how a majority function looks. And this is how we can express a majority function as well in terms of OR and AND. So depending on what's the value of this C, whether it's 1 or 0, we will have an OR operation between A and B or an AND operation between A and B, right? The example was A and B charged, C fully discharged. If it's the other way around, A and B discharged and C fully charged, the majority would have been 0. Yes?
Then isn't what much more vulnerable to RowHammer?
That's a very good question. Yeah, it could become more vulnerable to RowHammer, and especially because in this so in this design, in this ambit work, because you need to activate 3 rows at the same time, you need to modify the row decoder, right, to be able to activate multiple rows at the same time. Row decoder, conventional row decoder, can only activate 1 row. So the ambit paper proposed to have a smaller row decoder that is able to activate 3 rows that are called the compute capable rows. And if you were using ambit in such a system, you would be activating these rows a lot, right? And in that case, it might affect the nearby rows, right? Well, that's true, but it's also true that it would be relatively easy to prevent. For example, with isolation rows, that is one of the ways of alleviating RowHammer that people have proposed, right? Because these rows are, in a very specific part of the subarray, we could have some isolation rows. Anyway, if you want a better discussion about the possible effects of RowHammer, I can recommend you a follow-up of this ambit paper that is SimDRAM. There is also a link in a later lecture, and there we have a short section where we discuss about RowHammer. But yeah, of course, I mean, this is this is research, right? So here we take a theoretical approach in order to prove these ideas. We run SPICE simulations, and these SPICE simulations show that this way of operating is feasible. This could be used in a real system. But of course, this doesn't mean that it's going to be 100% reliable computation. It might have issues as well. But still, if DRAM were designed to support this kind of computation, for sure it would be better than DRAM that is just designed for capacity. So I think there is a lot of work to do here to enable these kind of techniques, but we are showing that they are potentially feasible. Okay, so one of the things, and as you have observed in the previous operation with the majority operation, is that in the end you destroy the original values, right? If you activate 3 rows at the same time, when activating the sense amplifier, the 3 rows or the 3 cells will end up having the same value. That is the result of the majority operation. So that's why the ambit paper proposes to use row clone to copy data from the source rows to the some destination rows that are these designated rows or compute capable rows that I just mentioned, because you don't want to destroy all the data every time you use it, right? So that's why, first of all, you copy using row clone from one source row to the compute rows, then you compute, and at some point you write back the results somewhere else to a different destination row. In this case, it's called C. Okay, so these techniques were first proposed in a paper in 2015. That original paper proposes a way of doing and or, but if you want to be functionally complete and perform more complex operations, you also need to have not, right, or be able to invert the bits. And that was made in the AMBIT paper with so-called rows of dual contact cells. And as you see, they are dual contact because they have two word lines. One of them is, or one of the access transistors is connected to bit line bar in the sense amplifier, and this way you can read the inverted value. That's the basic idea. There could be also other ways of implementing NOT, and here you see more or less, the step-by-step execution of the NOT operation. The AMBIT papers showed amazing results compared to CPUs and GPUs or PIN systems based on HMC. Also very important energy savings, and also in real-world workloads, like, for example, this bit weaving with a performance improvement between 4 and 12%, even though not the whole application is executed in AMBIT, only certain operations inside the application. And this is the link to the paper, and this is a book chapter, extended one, that is based on the AMBIT paper as well. And this is the SIMDRAM framework that I mentioned as containing this discussion about RowHammer. I'm going to, skip the slides that I have here for SIMDRAM because I cannot go into the detail. We don't have enough time, but they are there next for your own benefit. But very briefly, to summarize what SIMDRAM is about, is a way of creating arbitrary any functions, any operations that you may desire to be executed inside memory using majority operations, same as AMBIT. It's possible to first of all, express the specific logic, the specific operation in terms of majority and not operations. Based on that representation in terms of majority and not, create a microprogram. And this microprogram, as you see, is going to tell the memory controller what are the commands, the DRAM commands that need to be sent to the memory chips in order to perform AMBIT operations or majority operations and not operations, and based on those majority and not, perform much more complex operations. So that's what the SIMDRAM framework is about. And you have a bunch of slides talking about many more details of SIMDRAM. It's a paper that we have also discussed in previous lectures, in previous editions of this seminar, and you can even see some performance results comparing. Yeah, there you are. Some performance results comparing to CPU and GPU, and very nice performance improvement. So this is the SIMDRAM. There are also other works from our group in processing using memory, like those related to security. For example, this one is about generating physical unclonable functions inside DRAM or true random numbers. This is another proposal for true random number generation, and this is an end-to-end system that supports true random number generation. And there are even more works. Remember that I talk about processing using memory with different memory technologies. This is a very recent example from our group that uses very similar ideas to AMBIT, but in this case in NAND flash chips, so in storage, or this other one that somehow improves on SIMDRAM and on AMBIT in order to enable lookup table queries inside memory without having to go out of memory. So these are the two approaches I don't know if you guys have any other questions. We are over time, but I'm going to finish in 5 minutes. There are these two key trends, processing near memory and processing using memory. It's still necessary to do some additional work to enable the adoption of processing in memory. And that spans applications, software and hardware for PIM, programmability, right? How do we have to program these systems, system and security support, runtime and compilation systems, and also infrastructures to assess the benefits and feasibility. For example, the PyDRAM framework that I explained or I introduced, or simulators or benchmark suites on many other infrastructures. So all of that can be solved with a change of mindset. This change of mindset spans the entire computing stack, but that must be the way of building fundamentally energy efficient and data-centric computing architectures that are also high performance, in summary, computing architectures with minimal data movement. So these are just some concluding remarks. The goal is to make systems better balanced, and this will allow us to create systems that are higher performance and higher energy efficiency by enabling computation inside or close to the memory. This can be orders of magnitude faster and more energy efficient, can enable new applications, and can in the end provide more sustainable computing systems. So yeah, basically fundamentally better architectures that are data-centric, data-driven, and data-aware. And we need to revisit the entire computing stack. So yeah, that's some basic principles to create systems that are more efficient, and that requires open minds. If you want a summary on processing in memory, a review on processing in memory, and also an introduction to all these kind of issues or all these things that need to be enabled to support processing in memory, I can recommend you our book chapter. We have talked about some of the issues and potential solutions to the issues in multiple talks, like for example, this special session that we organized in the IES-VLSI conference last summer. And you can find much more in our courses, such as the computer architecture course that now it's taking place on Thursdays and Fridays, and all these PIM course that I mentioned earlier. This is all from my side. I went 5 minutes over time. Let me know if you have any burning questions. If you don't have questions now, you can contact me later, and we can clarify whatever you need. Is there anything? Okay, so then we are done. Thank you very much for your attention. Enjoy the rest of the day.